Hello everyone, this is Dr. Diaz. Welcome back. Today we're diving into part 3 of chapter 5, Aqueous Reaction. This is one of the most exciting parts of chemistry because we get to see how substances interact in the water, sometimes forming solids, gases, or even life-saving compounds like bone cement. Let's explore how these reactions work and how to predict their outcomes. So let's start with the precipitation. Here is the first example that I gave to you when I start talking in this chapter 4 with the molecular kitchen. Remember that? This occurs when the two aqueous solutions combine and they form a solid. So the solid is called precipitate. And it happens when the product of the reaction is not soluble in water, meaning it doesn't dissolve and instead settles out. A classic example here is the reaction between lead 2 nitrate and potassium nitrate. So they will form lead 2 iodide and potassium nitrate. The lead 2 iodide is insoluble and forms this yellow bright precipitate over here. So this is a very common reaction, and we represent with the solid just to show you that we have precipitate here, and if it's a soluble one, we use aqueous because it is dispersed in the solution. Solid is for the precipitate because form a solid in the solution. Okay, so if you no precipitate form, we say no reaction. That's because all the ions stay dissolved in the solution and not new will appear. It's important to check solubility rules before assuming a reaction will occur or will not. So if all possible products are soluble, no precipitate form, no reaction. So to predict precipitation reactions, we need to follow some steps. First, we need to identify the ions. And then we swap the ions to form possible products. What I mean is, imagine if you have this. Okay, so CD. So we always start with cation and then followed by anion. So that means I have a positive charge here, negative charge here, and then I have positive and negative charge. So they can swap, so negative with positive, okay? So it can be AD and can be CB. This is negative. So then you balance the charge, write correct formulas. You always need to balance the charge. Remember, the summatory of the charge must be 0. And then you're going to use solubility rules to determine if any product is not soluble. If a product is not soluble, it will precipitate. If both are soluble, write no reaction. And don't forget to balance the final equation using coefficients, not subscript. So this is what you're going to do, and remember to change only coefficients. When I say that, is imagine if I have, for example, 2 sodium chloride or 2 water molecules. We cannot change the subscript over here. You only change this. So if you didn't have the chance to watch the last class, the previous class, chapter 2, how to balance equations, chapter 4, sorry, part 2, please review and I'll talk about this, okay? Because what you see over here is 2 water molecules. If I change the subscript, imagine if I'll just write down like this and I'm telling you that I have a 2. No, this is a complete different monster. So this is not water, this is another molecule, and will not change the subscript. The subscript is the identity of the compound, okay? So here again, just to show you how you exchange the pairs over here. So potassium iodide and the lead 2 nitrate. So see, this is the positive charge, this is negative charge, and then you're gonna swap and form new possible products over here. So let's see if you understand. Let's test your understanding here. Look at this problem, and I ask you to consider the generic ionic compounds with the formula AX and BY and the following solubility rules. So they say that this is soluble BOI is soluble, but forming a product like soluble and no soluble. So what I'm expecting to see is this one BX, right? And the bottle set out. So when I look at here, so I have BX over here, so in the bottle, and all the other are dispersed in the solution. Okay, so we have some elements over here, and then we have Y ions, and we have A ions in the solution. So this is my reaction happening over here, right? Because I see the precipitate. This shows the precipitate as AY, but AY is soluble, so will not precipitate, will actually be dispersed in the solution. So another thing is how you represent aqueous reaction. So we can represent the aqueous reaction in three ways. Molecular equations that show the compounds as if they were intact molecules, like you see over here, or complete ionic equations. And these complete ionic equations, you're gonna separate and show the ions, like I did over here with the potassium hydroxide. So if I have two, you're gonna have two of each ion, right? So, and we have non-ionic equations that show only the ions that actually react. So here is the complete ionic. So we separate all the ions. We cannot separate solids because they stay intact as full molecules, so will not change. So solid, liquid, and gas, we don't ionize, we don't separate, okay? So they will be intact molecules, like you see over here. All other ions we separated, see? We separate the ions, and don't forget, if you have two potassium hydroxide, I need to specify that I have two ions, cation, anion, and so on, okay? So in this case over here, I have magnesium nitrate. See, I have two nitrates, not two magnesium, so this is why I have two nitrates over here, okay? So, and this, when you write down the ionic equation, you're gonna just look and you're gonna notice that some ions appear unchanged on both sides of the equation. This we call spectator ions. They are present but don't participate in the reaction. We will identify them and remove them in the next step, so to produce the net ionic equation. See, over here, nitrate appear on both sides of the equation. So here I have the arrow that separates the reactants from the product. So in the net ionic equation, remove spectator ions and show only the species that change it, like you see over here. So the only ions that stay will be the one that is not repeating in both sides of the reaction. So the spectator ions that actually they come inside of the reaction and they come out just to balance the electrons over there, but they don't react. The same way they enter is the same way they come out. So summarizing, molecular equation shows all compounds, complete ionic equation show all ions, and non-ionic equation show only the reacting species. Each format has its purpose depending on what you are analyzing. Let's practice a little bit. Which of the ions listed below is a spectator ion in the complete ionic equation shown here? So please choose, look at the reaction. So see, we have the arrow over here. Look at both sides and check which one are repeating in both sides. So I can see silver is not repeating, so that's okay. Nitrate is repeating both sides, so I have both sides. And also sodium I have both sides, but in the list they show us over here, the only one that we show is the nitrate that is a spectator over here in this list, okay? So let's keep testing. So I have here example of the molecular equation. The first thing you need to see if the equation is balanced. So you're gonna check each element and the polyatomic ions if they are balanced, and they are. Then you're gonna write down the complete ionic equation. Remember, solid we will not separate. Okay, solid, liquid, and gas, we don't separate. So the complete ionic will be like this. So then you see that it's solid, I didn't separate. Then you're gonna check which one is the spectator ions. So I have the nitrate on both sides, and I have the potassium on both sides. So those are my spectator ions, nitrate and potassium. So to write down the ionic equation, so I'm gonna copy this and keep only the ones that are not spectator. So this is my formula, and this is what happened in my reaction for real. This is what changed. That's my product. Okay. So again, I'm using an example of a zinc compound. So let's look up there in this. So we have the solution over here. I need you to balance the equation first, and then, of course, I showed you before I wrote, but the first thing you need is to balance the equation. To balance the equation, you can use the same rule that I use in my last class, like start with the metals and then you go to the non-metals. So we have the reactants in the product. So we list all. This is the chlorine over here, and then we have sodium and hydrogen. So we have 2 sodiums on one side, 1 sodium on the other side. I have hydrogen, so actually here is opposite. I have 1 hydrogen and 2 hydrogen on this side, 1 1 and 1 1. So I can start with the sodium or the hydrogen. So we're gonna put a sodium. If I put a 2 over here in the sodium, I fix the sodium, but also now I have 2 chlorines, right? So when I look at this, I have a 2 hydrogen because I fixed the chlorine over here. Now I have 2 sodiums, 1 sulfur and 1 sulfur, so all balanced. So when you change, just pay attention to this. I have 2 sodiums over here. So I need to write down my equation and show that I have 2 sodium ion. And be careful with the charge. If you don't remember how you see the charge, the metals, like the group 1 and 2, is easy. So we know that it's +1 and +2 charge. So group 17, you know that is -1 charge. That is group 17 in the periodic table. Or group 16 in the periodic table going to be -2, right? But when you're not sure, you just some compounds, some elements, you can check with the ones that you already know, right? So I know that sulfur is in the group 16, so I know the charge would be -2. But if you don't know, look at this. I have 2 sodiums over here. You know that sodium is in the group 1, so it's +1. So when you see sodium +1, I know the sulfur is -2 because when we cross over here, look at this. I have this. See, this is the charge actually from the sulfur over here. This is an easy way to find out the charge, but be careful because we always find the short formula. Remember the empirical formula for ionic. So sometimes if you have a molecule that is A2B2, so I know the charge is +2 and -2, but my formula actually would be AB. So you need to know how to find your charge in a periodic table. Okay. So another thing here is besides the charge, pay attention. Here I have gas, so you don't separate that. Okay. Then you cut off what you have as spectator ions, and then you have your net ionic equation. Good. So in the 2 more reactions types, we have this acid-base and gas evolution. So we have acid-base reaction neutralize each other to form water and salt, and gas evolution reactions produce gas, often alongside water. Both involve ion exchange. So 2 other important classes in the reactions, as I said, is this. And we call this neutralization reactions because actually they neutralize the solution. Okay? So according to Arrhenius, acid produce hydrogen ion and base will produce hydroxyl ions. Okay? So when you see here, so I have a hydrochloric acid producing hydrogen ions and chloride ions. So here it's a base, sodium hydroxide, producing OH minus, or which hydroxyl ions. So polyprotic acids contain more than one ionizable proton and release them sequentially. The first one that will ionize is strong, while subsequent ionized protons are weak. Example will be phosphoric acid. So I have 3 protons that can be ionized. So will be 1, and then will be the second one. Okay. So these are called neutralization reactions. I explain why, because when they react with each other, they will produce salt and water. The net ionic equation usually shows protons and hydroxyl forming water. You will not see H plus plus OH minus. We put it together and we have water. Okay? And assuming that salt format is the soluble one. This is aqueous calcium nitrate over here. So as the donate protons to water, they forming hydronium ions. So hydronium ions is H3O plus. So bases dissociate to release OH, hydroxide ions. And acid-base reaction, proton from the acid and the OH will form water. Okay, so here we have a reaction of hydrochloric acid, sodium hydroxide forming water, and the salt over here. So here is a visual of an acid and base reaction. So watch how the ions combine to form water and salt over here. So we have a neutral solution over here. Okay. So the salt will be dissolved in water, so we have ions around. So let's look to the common acids and base. We have some weak acids as the formic acid, acetic acid, hydrofluoric acid. Those are weak acids. And we have 7 strong acids, which is the hydrochloric, hydrobromic, iodic, and nitric acid, sulfuric acid, and perchloric acid. Those 7 are the strongest acid. And I know that nitric and the hydroiodic acid we don't talk too much, but it's good to know which are strong or which one are weak, because they will form they are good electrolytes, so it's good to know. Okay, and we have some strong and weak base. Here is a way that you can memorize those. We have the strong base acids over here separated, and we have the strong base here, which is the alkali metals with the hydroxide ions like lithium hydroxide, sodium hydroxide, potassium hydroxide. All those are very strong bases. Calcium hydroxide, strontium hydroxide, and barium hydroxide are strong bases. They will dissociate virtually 100%. They are strong electrolytes. And the weak acids will not dissociate completely. So they will stay associated. And some will dissociate and some will not. Okay? So if you want to predict the product of the reaction, remember, we need to change the pairs over there. So here we have the hydrogen and we have the OH, so positive and negative, so they will get together. See? And we have positive and negative, so they will get together, forming barium chloride. See that I have this, the chart of this over here, right? Because hydroxide ion is negative, so I have barium chloride. So when you cross, look, will be BaCl2. This is the chart of the Ba over here, and they have the water. So the same thing over here. So when you lose this hydrogen over here, that is a donation. So right, in the acid reaction, they donate the proton over here. So it's separating. So I have two ions over here, positive and negative. So this will connect with the negative, and this will connect the positive. So this is the possible products. Okay. So don't forget to balance the reaction. Look at this. I have two potassiums over here, two hydrogens over here, and on this side I only have how many hydrogens? Okay, one, right? But I have this one plus this one. What is changed? So the best way is make a table. Remember, reactants and product, make a list, and then you check everything that you have. Okay, because otherwise you're gonna make some confusions over here. Okay, so I have two oxygens over here, plus one, I have three. I have one plus two, I have three oxygens, and then this side I have three hydrogens and three hydrogens. But now I have just one over here and plus two over here. So I have a 3 plus 2, it's 5. And here I have a 3 plus 1, 4 plus 1, 5. So I have 5 as well, right? So, and I have a carbon 2. I have a carbon 2. So you need to pay attention on this. This is not perfect, right? Because I have a 2 potassium, and here I only have 1. See? So you need to pay attention when you balance the reaction. Write down everything, because if you don't write down, you're gonna make mistakes. Okay? So titration in the lab is a technique to determine a concentration. You add a titrant to an analyte until they reach stoichiometric proportions. So the equivalence point is the stoichiometric proportion. So the point in the titration when the hydrogen ion and the hydroxide ion from reactants are in their stoichiometric ratio and are completely reacted. So an indicator is a dye whose color depends on the acidity or basicity of the solution. In this case here, we have the phenolphthalein, which is gonna turn pink if you have a basic solution. So when you start your titration, after a while you're gonna see the solutions getting a little of pink color, but then the color will vanish. So you stop when you have a very light pink for at least 30 seconds over there. That means you have your stoichiometric point over here. So the equivalent point. So here, see, when you see that it's getting pink, but when you shake, when you mix it, that color vanish, and then you put it just one more drop and you get a pink like that. So normally we want a clear, a pale pink, a little bit lighter than this color over here. So let's practice a little bit. Here I have a 10 milliliter sample of 0.20 molarity of HBr solution, which is titrated with 0.10 molar or moles per liter sodium hydroxide. What volume of sodium hydroxide is required to reach the equivalence point? So how are we going to do this? So first thing that you need to do is look at the data that you have, right? So first thing here, I have 10 milliliters, right? But I know that molarity is moles per liter. So the first thing that I need to do is to convert this to liter, my volume, so I can get moles. So I know that 1 liter is 1000 milliliters. So I can cut over here and produce a liter. And then I will multiply by the concentration, because this is 0.20 moles per liter. Then I'm going to cut up and I'm going to have moles. So in this math, I'm going to have 0.0200 moles of HBr, hydrobromidic acid, right? So then we have to write down the reaction. Look, I have NaOH and I have HBr. So this can get together with this and this with this. Remember, swap the ions. So what I'm gonna have is this NaBr plus H2O. Okay, so here what you have is water liquid and I have this. It's well balanced. So I have 1 per 1. So that means the same quantity of HBr, a hydrobromic acid, must react with the same quantity or moles of sodium hydroxide because they're 1 per 1. So I have 1 sodium hydroxide, 1 HBr over here. So now I need what we need. We need 0.0200 moles of sodium hydroxide. Okay, so the volume required will be, okay, so I want a volume. So I have the concentration over here, right? What is the concentration? 0.10. So that is moles per liter, right? 0.10 moles per liter. If I want a volume, I'm gonna flip this and I'm gonna use 1 liter divided by 0.10 moles. So what I'm gonna do here is liter per 0.10 moles, and I will multiply by this. So you're gonna fix, cut off, cancel out, and you're gonna have the volume. So the volume will be 0.0200 liters or 20.0 milliliters. So the answer is this one. Good? So first you need to find the moles, and then you check if your reaction is 1 per 1. So then you convert the moles that you needed to the volume through the concentration that you have. Okay? So the gas involving a reaction. Some reactions produce gas directly and other form a compound that decomposes into gas and water. These are common in acid-base reaction too. So here is a visual of gas evolution reaction. So we have here sodium carbonate and the hydrochloric acid forming water and sodium chloride plus CO2. So we have a gas over here. That's why you're going to see some bubbles. That is indication that we have a reaction happening with the gas formation. So this table shows different reactants in the gases they produce. Like sulfides will not produce intermediate products. They will have gas involved. And carbonates and bicarbonates will produce CO2. Sulfides and bisulfides will produce SO2. Ammonia will produce ammonia. So those will produce some gas, and this is good to know. Okay, that will help you to write down the reactions. So, and we have redox reactions that involve electron transfer. Oxidation is when you lose electrons, and reduction is when you gain electrons. These reactions are essential in process like respiration, combustion. So here we have rusting. So see, you have the oxygen over here. So we have oxidation reduction reaction or redox reaction. That is the name we use it. Okay. Here in the combustion is a type of redox reaction. So oxygen pulls electrons from other substance, like here from the hydrogen. So you produce. You will get, like this is a thief, like electron thief. This is how I call the oxygen over here, and they will form a reaction that we have, the redox reaction. Okay, so in this reaction, hydrogen and oxygen will react, form gases, water. So plus oxygen gas, so the plus some heat, actually, right? Because they're reacting with oxygen. Oxygen is one of the main reactants over here. So the fuel, which is the oxygen here, gives up electrons. Oxygen takes them, and then the energy released become heat and light. So the flame that you see over here, okay? So what you see actually goes from 0, because this is the redox, so 0 is the Knox number of oxygen, and here actually we have -2, so it goes to 0 to -2 over here. Okay, so in this case the oxygen is reduced. Okay, so a real life example, the combustion reaction in the human body. So you don't see flame over here. And a cellular respiration, this is a curiosity for you. If you're in the health science, you're gonna love. If you're an engineer, you're gonna love as well. So even though we don't have flames inside us, our bodies perform controlled combustion reaction every single second. The process is called cellular respiration, and it's chemically the same type of reaction that we use to burn fuel, just slower, safer, and enzyme controlled. So we have here glucose plus oxygen. They will produce CO2, water molecule, and some energy. So this is what happens in our body. This is how important is our chemistry and all in everything. In health science and engineering, chemistry is so important. So an oxidation and reduction reaction, or the element that suffer oxidation lose electrons, while the one that suffer reduction will gain electrons. In this case here, sodium is lose electrons, so will have oxidation. And here chloride is gaining electrons, so suffering reduction. So if it is reducing, if they are reducing, so they are the oxidizing agent. If they are oxidizing, actually they are the reduced agent, because they are making this reduce. This is making this oxided. Okay. So electron transfer does not need to be a complete transfer. So even if electrons are then fully transferred, uneven sharing counts as a redox. For example, hydrogen bonding to chlorine, they shift the electron density like you see over here. So now I have the hydrogen lose electrons density, and see that it's bigger in this side because I have more density for chlorine or chloride ion, okay? Because chlorine gains electrons density because they suffer reduction, okay? They got electrons. So, and also we can have a redox without combustion. Not all redox reaction involves fire. You saw the example in our bodies as well. Many happens quietly, like metal corrosion, the rusting, right? Or biological process, like cellular respiration. And this example here, we have a sodium, solid sodium, and I have a chlorine over here. Also, we have a gas, chlorine, right? And we'll produce sodium chloride, a solid. So electrons are transferred from sodium to chlorine. So to chlorine, forming sodium chloride. Sodium is oxidized and chlorine is reduced. So the sodium atoms are compactly arranged in the lattice like you see over here. So each chlorine molecule exists as two merged spheres. So the electron transfer results in a solid comprising of alternating sodium plus chlorine minus ions, or chloride ions, compactly arranged in lattice structure. Okay? So when metals react with non-metals, they will form ions. This is a classic redox scenario. Electrons are transferred. And we need to track those. To track electron flow, we assign oxidation states. This imaginary chart helps us understand the redox reaction. Follow the rules to assign them correctly. So we're going to find the oxidation number. First, we need to know that oxidation states are imaginary charts assigned based on a set of rules. They are writing with charge before magnitude, for example, +1 or -1, or ion charge are real measurable charges, like they are writing with the magnitude before charge, for example, +1, -1. So the following rules are in order. Free elements have oxidation state 0. Like copper is 0, chloride is 0. Monatomic ions have the oxidation state equal their charge. So that is good. So you know that group 1 and 2 will be +1, +2. And you know that when you have group 17 will be -1, -2, and 16. So the sum of the oxidation states of the atoms must be 0. Okay, so I know that hydrogen is +1 and the oxygen is -2. So if I multiply this, I have +2 plus -2, which this is the summatory, and it will be 0. If you don't see any charge around the molecule, you know that the charge must be 0. So the summatory must be 0. So rules for assigning oxidation states. So we have here continuum. So we're gonna have a lot of rules, but I'm gonna reduce that for you. With practice, you're gonna memorize every single rule. So the sum of the oxidation states of all atoms in polyatomic ion equals the charge of the ion. So here I have a -1. So the summatory of the charge must be equal -1. So I have here 3 oxygen, so 3 times -2 over here, and I have +5 for nitrogen. So when you add all together, I'm going to have -1, which match with the charge of the polyatomic ion. So group 1 metals have the oxidation +1 and all of their compounds, and group 2 +2, as I said before. So if in the compounds, non-metals have oxidation states according to the table. Fluorine is always -1. Hydrogen will be +1. Example here with the water is +1. Oxygen -2. Okay, and group 17 or 7A is -1, 6 -2, 5 -3. And you know that because we talked about that when I talked a little bit about the periodic table, right? So when you assign oxidation states, keep this point in mind. The oxidation states of any given element generally depends on what other elements are present in the compound, except group 1A and 2A metals that have fixed charges. When following the hierarchy, so in rule 5, give priority to element highest on the list and then assign the oxidation state of the element lowest on the list using rule 3. When assigning oxidation state to elements that are not covered by rule 4 and 5, such as carbon, use rule 3 to reduce their oxidation state once all other oxidation states have been assigned. I know this is confusing, this is why I have a resume over here. So a neutral atom of an element will always 0. Monatomic ion equal the charge. Ions in an ionic compound like sodium chloride also equal to the charge. The sum of oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge of the molecule or the polyatomic ion. Oxidation number for common non-metals like hydrogen will be +1 if it's bonded with a non-metal, or -1 is bonded with a metal, like over here. Oxygen in a compound will be -2, only -1 if it's a peroxide, like here. This is a peroxide, but it's not common. Halogens, when not central atom, So what writing first, like here, okay, so will be -1, or if they are bound with the oxygen, also will be -1. So let's practice a little bit so you can understand better. Let's first find the oxidation number of nitrogen in all those three compounds over here, polyatomic ions, and they have a compound NO2 over there. So first one, have ammonium ion. So the summatory charge must be +1, because this is the charge of this polyatomic ion. So I have +1 for hydrogen, remember, always +1. And the total from hydrogen will be 4, because 4 times +1, yeah, will be 4. And the overall charge must be +1. So nitrogen must be -3, right? Because the summatory, look, if I don't know the nitrogen, I'm gonna write an equation. So X +4, and I need the total +1. So when I pass to the other side, look at this, -4 will be -3. So that is the chart of this. Okay, so let me erase because I have my other math over here. So let's go to the other one, other polyatomic ion. So we have a nitride ion. So we know the oxygen is -2. So 3 times -2 is -6. The overall charge is -1. So the summatory must be -1. So I know that nitrogen here in this case must be +5. Because +5 minus 6 will be -1. Let's go to the last one. So nitrogen dioxide. So we have the summatory charge 0. So I have the oxygen is -2. So it will be -4 because I have a 2. 2 times -2 will be -4. Overall charge must be 0. So the charge of nitrogen will be 4. Good? Okay, we have some cases that we really need to write down equation, like in this. So if you need to find the oxidation number of the selected element, how are we going to do? So I know the potassium and I know the oxygen, right? We know the hydrogen and we know the oxygen over here. And you need to pay attention if you have a charge. In this case, we do have. So let's go to the first case. So we know through the Knox rules that the charge of oxygen is -2 and potassium is +1. Because potassium is in the group 1, remember? Group 1 is always +1. So then you're going to write down a formula. Look, an equation. 4 times 1. 2, I'm going to use V to identify my element. 7, instead of write down vanadium, just V. 7 times -2. So this is my formula and my equation, sorry, and I'm going to find V, which is +5. So let's go to the other one. So in this case, +5. The other one here, we know for the rule that we have a -2 for oxygen, +1 for hydrogen. So make it the same thing. We draw an equation, and you're going to find the sulfur, +4. Okay? Pretty easy. Let's keep doing. So which statement best describes the difference between the charge of polyatomic ion and the oxidation state of its constituent atoms? For example, the charge of nitride is -1, and the oxidation state of its atoms +5 for nitrogen and -2 for oxygen atom. So what that means? The charge of polyatomic ion is a property of the entire ion, while the oxidation states are assigned to each individual atom, or the oxidation states of the ion is the same as this charge. That's not, right? Even this is showing that is not. The charge of polyatomic ion is not a real physical property, while the oxidation states of atoms are actual physical properties. It's a lie. So this is the true one. So the charge of a polyatomic ion is property of the entire ion. So that means the charge over here is for whole polyatomic ion over here, okay, for the whole nitrate. So in the oxidation reaction, like you saw over there, oxidation is increasing in the oxidation state. So it has 0 to 4. See, it's increasing. And the reduction, decrease in oxidation state. So here I see the carbon is losing electrons, so it's oxidized. So this is the reductor agent. Okay, and this one is the oxidizing agent. Okay, some books will be reducing agent and oxidizing agent. So carbon lose, sulfur is gain. Okay, so the reactant that causes reduction and another reactant is called the reducing agent, while the one that is causing oxidation in another reactant is called oxidizing agent. So in this case, sodium oxidizes while chlorine is reduced. So sodium is the reducing agent and the chlorine is oxidizing agent. Good? So any reaction in which there is a change in the oxidation states of atom and going from reactants to products, that's a redox reaction. In a redox reaction, the oxidation agent oxidizes another substance and is itself reduced. The reducing agent reduces another substance, so it is itself oxidized. Which statement is true on this? Press stop in your video and try by yourself. A redox reaction involves either the transfer of an electron or change in the oxidation state of an element. If any of the reactants or products in a reaction contain oxygen, the reaction is a redox reaction. In a reaction, oxidation can occur independently of reduction. In a redox reaction, any increase in the oxidation state of a reactant must be accompanied by a decrease in the oxidation state of another reactant. Yes, you're right. D. So, and we have a combination reaction, which is a type of redox reaction. So they combine together, so we have two or more substances that react and they will produce only one product, like we have here, magnesium oxide, and we have ammonia, we have another product over here. So all this, we have a combination reaction. So when you have two or more substances that put those together and form just one molecule, like you see with the MgO over there, we have a combination reaction. The MgO is the magnesium oxide. So if you're not good on namings and nomenclature, please review the previous class. So bond cement formation, this is a curiosity for you. This comes from combination reaction, and actually it's a redox reaction. So we have doctors often use bond cement made from calcium hydroxide and phosphoric acid. These two substances undergo combination to form calcium phosphate. Okay, a key mineral found in natural bond. So this reaction mimics the natural mineralization of bond. The product calcium phosphate and is biocompatible and it helps repair fractures, fill bonds, defects, and anchor implants. It is used in dental surgery, spine fusion, and trauma care. It's a very nice reaction over here. So in the decomposition reaction, we have actually one substance that breaks down into two or more substances. Like we have calcium carbonate that is decomposing, and carbon dioxide and calcium oxide. So and the other equations over here. Okay. So and we have a good example in the decomposition reaction that is airbag. So how that works. So when a collision is detected, an electrical signal triggers the rapid decomposition of sodium azide, which is over here. So forming very fast products and produce gas, nitrogen gas, that will inflate the airbags in milliseconds. Okay, the sodium metal form is highly reactive, so it's quickly neutralized by other compounds like potassium nitrate and silicon dioxide inside the airbag modules to prevent hazard. This is a fast exothermic reaction and it produces a large amount of gas, perfect for inflating airbags instantly. And we have the single displacement reaction as well. There's our reaction when one single element will replace the other. In this case, replace the silver over here, forming copper nitrate and to silver alone over here. So it's always someone going to be alone. So we have a single element over here and a single element in this side as well. So the reactant and product. So the more reactive will replace or displace the less active metal in a compound. So in this displacement reaction, for example, silver ions oxidize the copper metals. So we're gonna have the silver gonna be by itself on the other side. Okay. So here you're gonna see that we have a redox reaction. I'm gonna from copper that is 0 because it's a single element, neutral element that goes to copper ion +2, and I have a positive 1 for silver on this side and 0 on the other. So here lost electrons, so copper was oxidized. This is the reducing agent, and we have the here +1 to 0 actually is reducing. This is the oxidizing agent over here. Okay. One other example of redox reaction, I think this is the third example that keeps you alive, is the oxygen transport in your blood. So here we have the heart of this process is the reversible redox reaction between iron 2 and the hemoglobin and the oxygen. So here the oxidation is the iron and the hemoglobin is oxidized to iron 3. So we have iron 2, the oxidized and iron 3 when it binds with the oxygen, and reduction when the oxygen is released to tissues, and so iron 3 is reduced back to iron 2. This redox cycle allows hemoglobin to pick up oxygen in the lungs and release in the tissues, keeping cell alive. So see, chemistry keeping you alive. So to know that if a metal will replace the other metal in a reaction, we need to look to the activity series to determine the spontaneity. So it's a table that lists metals in order of decreasing tendency to lose electrons. So, and this is the list of activity series. The following list provides activity series from the most reactive, the most easily oxidized and strongest tendency to lose electrons, and to the least reactive and most difficult to oxidize or least tendency to lose electrons. Actually, you don't need too much memorization here because we already talked about the periodic table and some groups like group 1 and 2, their metals very reactive, so they will oxidize easily. So we can use those tables to predict if the metal will oxidize when they are with other metals like over here. So which metal is most easily oxidized over here. So we can use the table. But if I don't have the table, I'm going to look to those and I know that sodium is in group 1. And I have a chromium and gold that is not in group 1. And so I know that group 1 is one of the most reactive metals that we have. So if you see over here in the list, you're going to see the sodium right on the top over here. And then we have the gold down there and the chromium over here. So I know that sodium is the most easily oxidized. I can give you other examples over here, like how to predict if whether or not a reaction occurs for each of the following. Imagine if I have aluminum foil, which is added to an iron 2 sulfate solution, or iron white is added to an aluminum sulfate solution, or manganese metal is added to acetic acid. How am I going to know if that will be a reaction or not? This is pretty good to know when you talk about materials, if you go to engineering course mainly, but also in other areas like health science, this is very important. Look at here. So if you see aluminum is up here, this is another type of table. now in this case, I'm showing that the most reactive over here, right? So is to oxidize actually is the same thing. So we have the easy to oxidize, and those the one that is not oxidized. There we have the symbol on the first table, and here have the full name. Okay. So we go to aluminum over here is in the top, so easy to oxidize and compared to the iron. So that will be a reaction, and the aluminum will replace the iron. Okay, will displace the iron from the solution. So a single displacement over here. So when you go to the B, was iron added to aluminum sulfate. So iron is not as strong as aluminum, so iron will not be able to displace aluminum, so that will be no reaction. Okay, so here we have another one. So manganese metal added to acetic acid. So when you talk about acetic acid, we're talking about the hydrogen that will be the positive charge over here. So, and the manganese is stronger than the hydrogen, so a reaction can occur and will replace the hydrogen, and it will produce hydrogen gas that will bubble from the solution. Okay, that's it. That's all. Bye for now.